Okay, good evening once again. Welcome you all to the session 4 or the day 4, and this is going to be a part 1 session. So today we have two presenters, one being myself, and then we also have Tavish, who will be taking the part 2. And so let's get into the part 1. I mean, there's no housekeeping activities today because it's all the same thing. And the only one request is that please join in on time, respectful of everyone's time here. All right. Okay. So today's topic is about like data engineering. I will cover pretty much the data strategy for SLM building, and then mainly from a data strategy perspective. And then Kavish will be covering more about the technicalities involved in the data engineering part of it. So why the data you choose matters more than the model you build. It's a very important question, and you have to ask this question to yourself because how to choose it like an engineer. If you're going to be in the engineering part, in an SLM building part, this is a very important question that you have to ask yourself. And so we will definitely go over this in detail in this part of the session. So before that, let me also introduce myself. My name is Venkateshan Nadimuthu. I go by Venkat. I'm a PhD student at Artificial Intelligence Institute of South Carolina, which is technically part of University of South Carolina. And I'm also a principal enterprise architect at a leading global pharma distributor company. I'm trying to admit some more folks here. Okay. So I have over about 18 years of experience and playing a role of an enterprise architect, mainly from a technology strategy perspective, more into the cloud and AI world. So my research focus in terms of the PhD is that the composite AI, working in the field of enterprise AI, how do we make that enterprise AI into the SDLC workflow? Neurosymbolic architectures. And I'm also leading the effort in terms of small language models at AISC for mission critical and enterprise AI applications. And I'm sure that you are aware that I'm also leading this SLM bootcamp, SLM++ bootcamp for IRO. So as you could see that, the AISC, I'm a PhD
So,
student.
Venkat, are you sharing the screen?
I'm not. I'm so
No,
sorry.
no, you are not.
I'm sorry. So when you become a host as well as the speaker, these problems happen. All right. Okay, now you should be able to see my screen, probably, right?
Yes, yes.
Cool. Okay. Now I just covered the title slide in terms of the data strategy for SLM building, and I'm just introducing myself. So if you have not missed anything, I would say like you just admit people. Okay. All right, so this is about me, and I have my LinkedIn profile, so you can take a look into it. And if somebody wants to join, please join. All right. Okay. So again, take a step back, read these two lines, because this is the intuition for our session today, right? Two students, same brain, same study hours. One student reads the textbooks, one reads the tabloids. So tabloids is like something like small, compact, many pictures and so on, right? Who passes the exam? If anyone would like to comment in the chat line? Raju, I'm not seeing the chat line. Probably you are seeing that. Tabloids, okay? Just one. Okay. So at the end of this course, at the end of the session, you will come to know which one is better, right? Either reading a textbook, like more of a raw textbook, or the tabloid version of it, right? Here, your SLM is the student, right? And you write its reading list. So that is what we are going to cover as part of the data strategy today. Okay. As I mentioned, that I'm not going to cover more about the technical stuff, which is Tavish. We have an expert in that area. I'm going to be talking only about from a strategy perspective. So we'll cover, this is going to be an agenda, like this is what we're going to cover in the data strategy section. So why data strategy is your highest leverage decision. And we will shortly discuss about scaling loss. How much data does a small model need? The end-to-end data pipeline, step by step, at least from a concept perspective. Does your SLM need linguistic data? And we will discuss if required. When I say linguistic data, like, to form a coherent text. And then we'll talk about the synthetic data. And we'll discuss more about it, like why synthetic data is needed, the do's and don'ts, and then also takeaways. And also we have an expert in this call, who's like Rajvi, who's very specialized in data strategy, data curation. And she has put in a lot of efforts in preparing a guide for you, all of you, right? And I think, I'm not sure, like whether Annapurna, sorry, if you joined the call. So the question that you asked yesterday, that what do we need to learn from this? So this is probably the first session that you need to focus on. This is your, this is all about data strategy. This is your first step in the process. And also I wanted to ask another question here, right? How many of you selected your use case for building an SLM? You can probably just raise your hand and then go down. Have you decided on your the use case for your SLM? See only one hand.
One in the chat box.
Okay, tentative. Okay, that's good. Okay, perfect. And how many of you, you can probably go down. Okay, so how many of you have your data set ready for your SLM building? Oh, perfect. Okay. Okay, so that's probably a raw data. So probably this session will cover like how do you go from raw state to curated state, right? So that probably we can cover it up. Yep, we'll take any questions on Q&A sessions at the end of the data strategy section. Okay, probably. Okay, so, and this is the learning objectives that we are planning to cover as part of this series. So explain why data beats architecture, design a data pipeline, and judge what data your SLM needs. And here you could see that argue with evidence from published models why data quality is the highest leverage factor for an SLM. So we will definitely go over it. And this is the steps. And this is where it's saying that whether your model needs general linguistic data or not, that we will be discussing more about it. Okay. So maybe this is your one slide that you wanted to take home or create a mind map for your whole data strategy, for your data preparation. And you could see the different order that we are covering it as part of this lecture, and you could see that where it is being covered as well. So define the job, right? So SLM, whether it is going to be at the end of the pipe, like I think Dr. Deepak mentioned, like, can we create an application or a chatbot? Like, is it going to serve as an end of the pipeline, or is it going to be part of the pipeline? That it is not going to be involved in generation activity. It is just going to be part of the pipeline, right? So you will see that define the job will help you explain about whether it's going to be a generator part or a pipeline component. And the great analogy would be like, in the restaurant, waiter and a kitchen staff, right? Waiter, you need charm, just charm to greet the customers and so on. The kitchen staff need the actual technical skills, the cooking skill. And evals before data. right? I know that you, in the procurement of data, you will be collecting the data, you'll be crawling the data, you'll be doing things like that. But make sure that you have your evals before data preparation, because you should know how will you grade the dish before you buy the ingredients, which will help you to get the finer ingredients, finer taste, all these parameters that you wanted to achieve as part of your meal, for example. Size the budget. I know everybody is very familiar with the Chinchilla, that 20 tokens per parameter. And we are going to discuss more about it from a scaling loss perspective. So greater than or equal to 20 tokens per parameter than overtrain. So we will talk about that specifically on that particular, I would say like the scaling loss. Source and curate, right? And so again, this is a kind of a step-by-step process from how do you source the data, how do you go to the 9 yards of the process to get to the golden data for your model training. And mix and order. It's very important again. Like, what is your mix? What is the, when you have a data set, when you're talking about data set, what is the mix that you should have in your data set? There's a great analogy here I mentioned here is that a balanced diet, a planned meal by meal, right? A balanced diet is basically, probably, I don't have to give an explanation there. It should be a balanced diet. And ablate and freeze. Just change one thing at a time. Use proxy model to text it out, and then you can you can scale it up to a billion parameter model or something like that, right? Change one ingredient at a time. So Tavish will go very deep into that in terms of how the proxy model, the paper, if you want to go into like Durami paper, then we'll be discussing it over as well. So this is follow this 1 through 6 step, which is very important for building your own data set. Okay, so with that, we'll move into why data strategy matters. So if you have seen that, this is an evidence that I wanted to share with you in terms of Phi 1, probably you all know about it. This is a basic from the most basic Python code, like the MBPP benchmark. Phi 1, which is a 1.3 billion model. And you can see that 540 billion model, which is Palm Coder. It's much smaller in size, 100 times of its size, not it's 100 times, but 400 times smaller than its size. And it's performed, like you see that the evaluation perspective, the human evaluation benchmark for coding, it has crossed the 45% for that 1.3 billion model, right? And so I think this is about 55% in human evaluation. The smaller model than this, which is 350 million parameter model, which has have that 45 across that 45% human evaluation benchmark. Right. I think no more person. I think I still see people joining in. Okay. So you got it now, right? So you see the code gen. I think this is probably from Salesforce. And again, Palm Coder from Google, and then Phi is from Microsoft. You could see that it's a smaller 1.3 billion model, but that beats a model 100 times of its size. You could see that this one is basically made up of 7 billion tokens total, 6 billion filtered textbook quality data, and 1 billion of synthetic textbooks. And I think it had 4 passes or 8 passes of it, and that makes like about 56 billion. So you see that the ratio that we will discuss more about it in the further slides, but just to give you that intuition of saying that so trained on curated data, which gives you much performance in terms of the model performance there. Okay, and if you want to have more reading about it, so there's a paper that I've attached here, and probably you can take a look into it. Actually, the textbooks are all you need, and this is very one important paper I want everyone to read before you kickstart your data strategy. I've given the reference at the end of this slide deck as well, so you can take a look into it, and if you have any questions, we can discuss. So what quality actually means, right? Because quality versus quantity is very important. Um, so, for example, whether a raw data, the common crawl will help you there, or a much more curated data will help you for an SLM. Because SLM, the term itself, it's called small, right? So it's not a large language model where you can bring in all the data, raw text, and then you train on it. So that's all. Like I think that is going to be extinct at some point in time, because people are going to be creating more and more small language models. And I think this bootcamp is also targeted at that we want to bring in like more and more SLMs. Either it could be domain specific or a task specific, a targeted model, right? That's what we are trying to teach here. So it has to be informative. It teaches something. It should explain, derives reasons. And I give an example of dietetics textbook chapter here. Clean, free of noise, no boilerplate ads like HTML tags, broken markup, repeated navigation, text, and stuff like that, right? Which will just swallow your token budget. It's not giving you any value there. Diverse, many voices formats, right? For example, if you seen one of the models here seen only one format, then you can only produce one format. So, but if it sees multiple formats like articles, Q&A, tables, dialogue, that will help you in terms of the model performance there. And then on distribution, it matches the job, right? How do you want it to, what is the target that you're looking for, and so on. So we'll go pretty much everything onto this one, like, in the further slides. So how to measure it? I mean, perfect perplexity of a reference model. You can use classifier quality scores, the dedupe rate. Dedupe is nothing but deduplication rate, contamination checks, and ultimately ablations on your own evals. So we'll definitely go deeper into this one. Filtering for quality buys you a 10 times smaller token budget. Right. This is a great example. If you know that the FineWeb data set, I think it is initially it was 15 trillion tokens, which is in FineWeb. But so they just added one step to this. They written down an educational quality classifier, which scores every page from 0 through 5. They have selected only the scores greater than or equal to 3. So they ended up from 15 trillion tokens to 1.3 trillion tokens. But you see the performance, models trained on the kept 10% outperform the models trained on everything. So that's a tagline. So quality filtering is compute you spend once and save on every training run after. This is a very important line. We'll definitely discuss more about it. So it's not about the training cost. It's about the inference cost that we'll discuss more into this topic there. Okay. So before we move on, right, can you say this in your own words? This is just a kind of an engagement activity, right? I want to make sure that I'm having you all with me for this session. So why a small model on curated data can beat a huge model on raw data? Maybe if we can write like one liner with short and crisp, and what a quality classifier does in a data pipeline. If anyone wants to come out of mute and then want to talk about it, that's totally fine. We'll just take one person and then we'll move on to the next one. More precise knowledge, focus only on what's needed. It'll be more specifically trained on that given particular. I think that I'm unable to read. Okay. Good. I think I have good understanding of why we need a small language model, right? I mean, otherwise you wouldn't be in this bootcamp at all, right? That makes sense. So this is very important part, because it's not that you just take all the data scraped from the internet, just put it for your data set, just go ahead and train it up. You may fancy, in a fancier way that you can say that I trained a model, but is it worth saying that you trained a good model? No, the answer is no, right? So we'll discuss more about it in further slides. So data scaling loss for small language models. How much data does your SLM need? Okay, this could be another question, right? How much data does your SLM need? So you know that Chinchilla has 20 tokens per parameter. Do you think that if you can go with the 20 tokens per parameter, does that satisfy your data part for the model training? You can say yes or no. That's totally fine. Yes, okay, great. So if you just have 20 tokens per parameter, that's more than enough. That's what it's saying. Yes for SLM, okay, yes. Perfect, yes, 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 yes. To your surprise, the answer is no. So I'll tell you why. Okay, good that I asked this question now. So now probably you'll be more attentive at the next slide. So compute optimal, right? Approximately 20 tokens per parameter. So as you know that this is just to talk about Chinchilla and before Chinchilla, right? So you know that the Copper model, which was trained on, like this is a 280 billion parameter, but the training tokens was like 300 billion. But that was a kind of a baseline. But if you see the Chinchilla, that they introduced that 20 tokens per parameter, the 70 billion, which resulted in 1.4 trillion token. This wins broadly. This is compute efficient, and this puts you into a training budget. So this is the scaling loss paper, and everybody started following that for large language models, pretty much, right? So this is the compute budget is a trade between the brain size, the parameters, and the books to read, right? The tokens they read. So before 2022, like if you know the GPT-3, it was only seeing like 2 tokens per parameter. So that was kind of a baseline, and that was a kind of a de facto standard. But after Chinchilla arrived, they showed the model, the data showed like should equally scale equally. That's when like 20 tokens per parameter was introduced. Okay. So the rule of thumb for your project, okay, this is a rule of thumb for your project, very carefully. 100 million parameter SLM wants greater than or equal to 2 billion training tokens. When I say 2 billion, which is probably the 20 tokens per parameter ratio, but that's not enough. That's the floor. Plan to collect 5 to 10 times more raw data. Okay, we'll see why we need that. Okay, to answer to your question straight away, yes or no question, this is a great example, right? So as I talked about, like the small model should train far past compute optimal. When I say compute optimal, which is that 20 tokens per parameter. So GPT-3 in 2020, like they used like 2 tokens per parameter, and Chinchilla introduced that 20 tokens per parameter. But if you've noticed carefully, Llama 3, it was 150 tokens per parameter, right? And another model, which is Mini CPM, model recipe, which is 192 tokens per parameter, right? So this is a little bit, deviating from what you were thinking about it, right? I should say myself too, at some point in time. So Chinchilla optimizes training cost, right? But SLMs exist for cheap inference. Probably this is a great idea to, great segue to explain why we need this. So you take an example of, so why we need an SLM? Because LLM, you can, in current environment, let's say an enterprise access to an LLM through a hyperscalers like Azure, Google, Microsoft Azure, Google, and AWS, for example. They host their LLM model. And what you do is that you go ahead and get that API credits to access those models. And the enterprises are spending about roughly minimum of 1 million per year in terms of the inference cost and things like that. So training was in kind of $1 million budget and things like that, but that's one side. But if you see the recurring cost, the lifetime cost, this is more on the other side, right? This is very, very important actually. But the SLM on the other side, if it is trained with like more tokens, the initial training budget, maybe it could be a lower parameter model, but with more tokens, it will save you the cost on the inference side. Let's say that you wanted to deploy it into a mobile phone. If you wanted to deploy it on an edge device, deploying it for an enterprise edge locations like distribution center, for example, or manufacturing facility or somewhere, it has to process multiple times, like millions, billions time, right? So you see the recurring cost or the lifetime cost, that's going to be phenomenal. So the LLM, if you understand the difference today, like LLM, the training cost is one part, but the other part is that your recurring cost. But on SLM on the other side, if you wanted to keep the inference cost very minimal, you have to make sure that the data that you train on should be far more optimal, right? Far more than that optimal point. So that is what we are explaining it here. You will have more and more examples in the further slides, which will affirm the statement that I'm making here. But so every rupee saved at serving time justifies more training. So simple as that. So accounting for inference pushes you to a smaller models trained much longer. And there is a paper that exclusively talks about that, and that is also available as part of the refresh. And please take a look into it. And if you want to have a debate over this, definitely we can have it, because it's a very good debate that we should have. Everyone in this bootcamp should have this, because our assumption is that, okay, 20 tokens per parameter, let's put that lower model, a smaller model, which will satisfy the condition. No. So this is the opposite of it, right? So the consequence of this one is that your data appetite is huge, which is why the rest of the session is about where the data comes from, right? That's why we're going to delve into that stages pretty much. Okay, cool. So in terms of the data, right? Because everybody's thinking about, okay, let me just automate my process. If you're working in an industry, like company, or even in an in the college world, right, the university world, right? So you may have some use cases coming in from companies around you, or you might be thinking about a use case, or somebody might be thinking about a use case in this particular bootcamp as well, that my data is very limited. What should I do, right? Ran out of domain text or task specific model, right? That you ran out of domain data. So what you can do about it, right? So that's what we're going to discuss more about it. But one other key point that you can have it is that up to 4 epochs of repeated data, that's equivalent to the same loss as the unique data. You can have a single forward pass or equivalent to 4 epochs, for example. That's allowed. But if you do more than 4 epochs, adding more compute buys nothing. So that's the concept that we are trying to say that. So value of each additional pass over the data is like after 4, it's of no value, and it's been discussed in the paper as well. You can take a look into it. So better escape hatches, right? Augment with adjacent domain or code data, rephrase or generate synthetic text. This is what we're going to cover in the next section. But you can see that, as I mentioned, like 5 to 10x more than the tokens per parameter required. So these are some of the 10 leading SLMs and the data design decision behind each. Okay, we have crossed 30 minutes actually. Okay. So 5.4 mini being very famous, about 4 billion parameters, and the targeted use case is about math and logical reasoning, and it's a heavy synthetic textbook curriculum. And Gwen 3, about 0.8 to 9 billion, and it's multilingual. So I've just given you this is just for your reference, nothing to learn more about it, but what is the landscape looks like, right? And from a small language model perspective. So none of this one on architecture. That's a very important point that you need to note. Every strength on column 3 was bought in column 4, right? Deliberately the data strategy. So that is why I'm saying that the data strategy is very, very important for your model training. The model training is like people like Tavesh and Keshav, that they have that OLM component. You just bring that OLM brain, just feed the data, get that hyperparameters configured, you get your model spit up. the data, what you feed in, is very, very important for your model training. So this part 3 is going to talk about the end-to-end data pipeline. And again, so eight steps are very, very important. So this is mainly from a concept-wise, and Tavish is going to go deep dive into it. But this is for information like, you need to source your data, either it's going to be a crawl data, corpora, licensed, and domain text. Filter, so you go for the language, heuristics, quality classifiers, and so on. And then you go to the deduplicate process. We talked about exact, near, duplicate removal, and clean. You have, sometimes you might have like PII, PHI information in the data that make sure that you remove that, the PHI or PII data from that, sensitive data, I should say. And iterate, like as I mentioned, use proxy models. If you're planning to build a billion parameter model, maybe you can train something on million parameter model, like 100 million parameter model, make sure everything is working as expected. Then you just move on to the 8 billion, a billion parameter model, and so on. Just change one thing, rerun the loop, make sure that everything is working as expected, transfer it. We have an example to cover that as well. Evaluate, right? Ablations on small proxy models. That's very, very important. Order, this is very important. Again, order is very, very important in your the pipeline process. And then the mix also, domain proportions and weights is also very, very important actually. So this is a great example of FineWeb, which was a 15 trillion token, but FineWeb ADU is like 1.3 trillion token. So you see that exactly that they've gone through this pipeline step. And this is also explained in detail in the paper that I mentioned here as well. Okay. So this is this is a very important session for you to get started into your first step in the process. So I know I've seen some of you have a data set ready, but some of them are still not in that phase if you're getting started with the data strategy. So these are some of these areas where you can source the data. Where tokens come from is basically like curated corpora, like you have the pile, the FineWeb, textbooks, and the other areas like where you can, the common crawl, for example, you can get that data. And then license and institutional. So you may have some copyrighted content or something like that. Make sure that you just respect, copyrighted information, sensitive data, license, and things like that. It's very, very important. And let's say that if you're creating SLM for your institution, for example, and you're using an institutional knowledge, and then with proper license and things like that, it's not going to be exposed to outside of your institution. That's a trade-off, right? So, but if you're going to put it into public internet, then you have to be very careful about license and institutional data as well, right? So there are two sets, how do you see the data? That's very, very important. So, you can take the decision, right, based on this conversation. Domain communities, right? Forums, Q&A, wikis, like a lot of ready data available, like in terms of a customer centric, you can have a lot of call center data, things like Kisan call center, for example. A lot of domain communities are available where you can take the data, real-time data. How do you curate the data and things? And then raw web crawlers, it's like a common crawl and filter hard and stuff like that. So I'm just taking some example of that, because my specialization is all about food and nutrition and agriculture. So dietetics textbooks and nutrition course notes, that textbook, so call it as a textbook spine. Food composition databases and dietary guidelines for the facts and tables, cooking Q&A and recipe text. These are some of this example, but you can design how you want to source your data, and then you can act on it. And again, evals are very, very important as well. Okay. So this is about the next step in the process, which is a filtering. Like we are talking about two sieves. One is a coarse and then the fine. So heuristic filters are like cheap. The first filter that you can apply, you can identify the language identification, because you are trying to be language that, like, English is going to be your target language for your model. Then you can only focus on the language identification, right? And if you're thinking about like Indic languages, that totally changes the game there. So you have to be careful about what language that you are training the model on. And so it just gives you an example or a strategy in terms of how do you filter down the data. So length, the symbol to word ratio, repetition rate, there could be some URL block list, adult spam domains and things like this. You have to be very careful about just filtering out the data from that aspect of it. And there is a paper that talks about the refined web, how this has been completed in with the web only data match. And then the second one is about the precise model-based filters. So this is where that classifier comes into picture. And I think Tavish is going to cover about one specific classifier for how do you do this classifier scores, and depending upon that you do a filter. And so trained on LLM annotated examples. So FineWeb and FineWeb EDU is a great example. Threshold your quality versus quantity. I think I mentioned this before. So very important, quality versus quantity. Right? So for LLM, you can just get all these things and then go into it, and that leads to hallucination, for example, sometimes. And this was where that human vetted, highly quality, high quality data, curated data. So it's very, very important that you need to consider for your filtering process. So that there's an example here. Datacomp LM found the quality classifier was the single highest impact pipeline choice that they did, and there's a paper attached to it. And yeah, so you can also see that, right, for your domain, especially I'm again focusing on the food and nutrition here. Is it genuinely about nutrition science or a general text, right? So it's not that, okay, I have only, let's say, 1 million token, and with that I cannot do anything about it. What should I do? Let me just go out and do a call data and then put it together and make sure that, okay, I have enough data to train that model. No. If you want to take if you wanted to spend more time in creating the data, that's totally fine, because that's going to decide your model performance, because being a model being small, and so as you also know about it, that we don't want it to have a repetitive information there. A lot of technical things that we can discuss about it, but from a data strategy perspective, make sure that it's take the curated corpora. That's very, very important. Again, so this is a great example, right? So same document 400 times is not 400 documents. So, okay, I wanted to increase the token size. So let me just copy paste the same thing 20 times so that I reach that corpora. Maybe you can do it for your exploration perspective, but that's not, should not be your ideal goal for your SLM building. That's very, very important, actually. Okay, and so one is that it wastes the budget. So repeated tokens teach less each time. So you pay, but you pay the full price anyway. And amplifies memorization, right? So instead of generalizing it, it just started memorizing it. That's what we're talking about, the point here. And corrupt evals, right? It's definitely going to corrupt evals, because it says that your model is performing very well, but it just inflates the scores, but it's not helping you, because it's not, I would say, like, it's not generalizing it. It's not doing the pattern learning there. It's just memorizing it, and it just gives you the score, but it's not going to help you for the long run. And this is about the exact and near, the document hashes and min hash. And I think Davish is going to cover this in deep there. But these are very, very important things that you wanted to take a look into it to avoid the repetition and things like that, right? So, and decontaminate. So decontaminate is a great example. They have used it in the Durami paper. That how much how much faster, like in the model. I think we will discuss in the future slides, actually. This is the last the cleaning process, right? In terms of the surgery inside the documents you keep. So basically, that it's not that every document you have, don't review it, you just put it into your data set. Make sure that you just go through that data set, because that is where we are saying that if it's a smaller model, you have the leverage of going deep in the weeds, making sure that you spend a lot of good time. You can spread it into teams. Maybe if you're working on a for your organization or for your institution, for example, make sure that you spend time for that the data cleanup. And I think there are a lot of tools available in the market today, or some Python libraries that you can use to do that cleaning process. So mainly that, strip the boilerplate, redact PII, and normalize your data set for sure. So the filtering decides which documents live in your data set, and cleaning decides which lines within them do. Right? That's very, very important. There's a difference between the filtering and the cleaning step. So keep this in mind when you're doing the filtering and the cleaning. Yeah, this is the point that I wanted to make sure that the Do-Re-Mi paper. So they did this on the small proxy model, and then they transferred this to an 8 billion parameter model, and you could see that it was 2.6 times faster. Right? So this is very, very important in terms of the better accuracy, reach the baseline 2.6 times sooner. So this is a mixture again. So we know hyperparameter is different from the data perspective, right? So just consider that mixture is also a hyperparameter, right? I mean, from a strategy perspective. So domain text, like think about that if you're trying to come up with a small language model on nutrition, food and nutrition, what should be your mix? The domain text is all about like makes up that 45%. General high quality web and books could be like 35%. The Q&A style could be like 15%, and code is going to be like 5%. The data tables and stuff, so on. So think about it. This is just an illustrative starting point, but you can think about like what is your target model. Again, then I talked about generator or part of the pipeline. So if it's going to be part of the pipeline, you don't need like general high quality web and books. If it's going to be at the end of the pipeline, you may need to have that curation happening. Coherent text generation should be happening there. So think about that as well, right? So I think that's what they mentioned there, generative, because if it's generative, then you need that linguistic skill is also needed, right? Because it's not that, okay, if I say proteins, carbohydrates, and fibers, it's not giving you any meaning. Hey, for a healthy meal, take 80% of protein. So I'm just giving an example, right? 20% of carbohydrates and 20% of carbs, and this would be helpful for your healthy lifestyle. So this is like kind of a coherent language generation. But if you really want part of the pipeline, you can just say that, okay, so this has 15% protein, this has 20% protein, and things like that. That's a different game there, right? So think about that and then go from there. I think so. This is again a tagline, right? So you don't need Do-Re-Mi this week, but you need the mindset: mix, measure, and adjust. Your UAS, you choose your right proportion for your SLM training, and go with that. Data strategy is an experiment loop, not a recipe, right? That's another important thing that you need to consider. Just choose your data, make it as a proxy model. Just go with the one run, change one time, one change at a time, evaluate, and then go back and then rerun your loop and things. It's an experiment. It's just not that saying that, okay, if I put everything there, it's going to work as expected then. So order is very, very important. Evaluate, small proxies, fixed evals, iterate, one change per run. So it's all been
Venkat, there is one question in the chat box.
okay.
What is the unit of the data, words or tokens?
Yeah, that's what the tokens, for example. Okay, so let's hold on to that question. There is that we have answered some of this information there. If you still have that question, we can definitely take it at the end of this session as well. So we have 14 more minutes. Let's try to cover the content, and you will also see that in the further slides. Okay, so hypothesis: adding Q&A data improves helpfulness. There's different formats. Ablation: 2 proxy runs, 1 variable changed, and then fixed evaluation suite, keep or revert, right? That's an important thing. That's just a kind of a workflow. It's very important that you follow this step to get your golden data, I should say. Yeah, so this is just a check-in again, right? Which step protects your benchmark scores from silent inflation? Can anyone say that in in the chart line, which step protects your benchmark scores from silent inflation? I don't see any answers. I'll just quickly cover this and then move on because due to the time constraint. So it's a decontamination, right? The dedupe plus cleanup steps. That's very important there because, for example, so your evaluation set has the question like which vitamin deficiency causes curving, the disease condition, right? And with the answer like vitamin C, for example. So now somewhere in like, if you have created like 400 GB data you scrape from the website, a quiz bank containing that exact question and answer. So you have the same question and answer, not one time, two times, right? So one in the initial stage and somewhere in the end of this or in the middle of this thing. You never notice that. It's one page in millions you train. So you evaluate, you scored 94%, you celebrate saying, oh, it's performing very well. But the model did not reason it's the way there. It just memorized the answer key. Basically, it has seen the exam paper. So simple as that. So very careful about it. And then, I mean, curated SLMs will give you very good results. That's the strategy. Okay, so this is the one which talks about, does every SLM need a linguistic data, right? So fluency is expensive. We'll only pay for it if your model has to speak. Probably you could infer from this, right? Whether it's going to be part of the end of the pipe or is it going to be part of the pipe, right? So end of the pipe, when I say that, okay, you get all the prompt, you're getting your context like RAG pipeline, and you're sending everything to the SLM and getting the response, then that needs definitely linguistic data to be trained on so that the vocabulary, the tokens, everything, the details, they're very, very important for you to generate that text. But if it's going to be part of the model, it is not going to be end of the pipe. So you just need to get some kind of a tagger, allergen tagger, and things like that. You don't need that fancy linguistic data, the general high quality web text for you to coherently create the text. So you can take the decision saying that whether this is going to be part of the pipeline or it's going to be the generator pipeline, right? So what teaches a model to write well, right? Again, this we talked about a little bit. So edit a long form prose, dialogue Q&A, explanatory writing. And what does not teach fluency is that this is about the structured data, right? When you think about, I have a lot of structured data, how do we deal with it? It's a tables, logs, keyword list, fact soups. They carry facts, but unstructured, but no sentences. So this is a kind of a delineation between what should be the part of your data set in terms of teaching that linguistic information. So small generative models spend most of their data diet on general text. The tiny llama, probably we might have used it or explored it. The 3 trillion, the most general tokens for a 1.1 billion model that speaks very fluently, right? That's and I have also given the paper reference here, so take a look into it. This is just to give you about the linguistic data. I'm sure that most of your models need linguistic data, but sometimes it's not always the case. So you have to be thinking about it like what is going to be your target. So yeah, this is against, maybe I'm too soon that I talked about this. This is about who does the talking in your system, right? If your SLM generates text users read, then you need linguistic data, general heavy, domain enriched. But if your SLM works inside a pipeline, like classifier, re-ranker, router, extractor, that tags like allergens and ingredient list, while a bigger model writes a reply, then you don't need like little or no general linguistic data needed. Train domain pure and representative inputs and so on, right? So domain pure and task shaped. So the question is never is linguistic data good? Does my model's output need to read like a prose? That's very, very important. But you can see how a lot of the trade-off, right? So whether if it's going to be part of the pipeline, you don't have to spend a lot of your tokens on the general high-quality text. But if it's going to be the generator pipeline, then you need a lot of this long prose and things like that, which will involve in generation activity. So this is again on the structured data, tables, the logs, knowledge graphs, and things like that. So part of the training loop, right? Whether you need to have that part of that pre-training data, this could be part of that, the context engineering part of it, right? So you have to be very careful about it. For example, like inventory, pricing information, like organization charts, and things that dynamically changes, like contractual quote and stuff like that. You can have a schema on things like that as part of your pre-training data, but not as part of your balances like prices as part of your pre-training data. This is something that you can take it for your reference for when you're curating the data set, because they go stale and cannot be corrected after training. So this is very, very important. Okay. So given an example for nutrition LLM, like train on how nutrients, food, and portions relate, but don't give that exact food composition database, right? Part of your pre-training data. That's very, very important that you can distinguish. So this is about the three nutrition SLMs, a meal plan writer, an allergen tagger, a cuisine router. Which ones needs general English and why? I mean, probably we can skip this one now, but you have a good understanding of it now, right? So this one needs a generator. This is part of the pipeline. Probably the cuisine router is probably part of the pipeline, but it's not involved in generation activity there. So synthetic data, right? And read this tagline. It's very, very important. The sharpest knife in the dryer. Very powerful, but it is easy to cut yourself with. Right? It's very, very important, to consider synthetic data. When do you go for synthetic data? Like when you run out of domain text, you don't have a lot of tokens. We're talking about 192 parameters, tokens per parameter and things like that. But where do we get that synthetic data and things like that, right? That's when, this section covers that. So there are ways to make the data, the distillation, self-instruct, rephrasing, real data, textbook style generation. So there are now the synthetic data generation is not quite heavy. I would say that now if you have if you have a strategy, you should probably able to create the synthetic data. I believe Rajvi has given that guidelines in terms of how do you generate the data and things like that. That's a very easy way of doing it, but that's very, very important in terms of getting that the token size. I think in one slide that we talk about that 2000:1 ratio, the Llama style model actually will go into that. So again, this is another thing that we're very careful about it, like a photocopy of photocopy fetch, right? Very important that this is the recursive training on model output erodes the tails of the distribution. That's very, very important. The model, it will lead to a model collapse. But be very careful about it. The bias amplification. So if you're thinking about distillation process, the teacher's blind spot become the student's confident errors at a scale. That's another thing from a bias amplification perspective. And then contamination perspective, right? So you have to be careful about it. The quality controls that you can have it in your side of the desk saying that anchor in real data, filter what you generate, and label a provenance, right? You just make a log of it, what you removed, and then you go for another loop and make sure that you get the golden data. Until you get the golden data, keep repeating any of the process to make sure that you have a golden data at the end of the day. So this is about the do's and don'ts, pretty much like, build your eval suite. This is something that we discuss in the whole chapter. Build your eval suite before your data set, deduplicate exact and near for every source, ablate one variable at a time, uses on small proxies, log provenance, license and pipeline version, and then read 100 random documents from every source, match the mix to the model's actual job. So these are some of the do's, and don't trust anything by the data quality claims that you haven't tested it out. If you don't have an eval suite, don't trust every data. So, okay, this is a good data, may not be right. So you got to be careful about that. And then check for contamination. Repeat a small corpus past 4 epochs and expect gains, right? Saying that, okay, I see a loss here, but let me run for 20 epochs, 30 epochs, so that I can get efficiency. No, that's not the case here. And replace real data with synthetic, augmented. Try to bring in more and more real data. Only if you're not able to do it, then augment it with a synthetic data. So these are some of the do's and don'ts listed in this list. This is for your reference again. So as I mentioned, like, this is your first step in the process. Make sure that you write your data spec before your next lab. I know that we have like five days week. The weekdays, you probably can take your time to sit down and write down your data spec. One page, your SLM's job, whether it's going to be a generator or a pipeline verdict. Target token count from the 20 plus tokens per parameter rule. 3 sources ranked by trust, starting mixture. So these are very important for your data spec. And if you can come up with that, and then that would be very helpful for you to get an efficient model trained. So audit 100 documents, sample 100 documents from your corpus with like some pandas library, hand label quality like 0 to 5, and do this kind of stuff. Like this is something for your help you with come up with the golden data. Run one ablation study in Colab, and now I think become for students especially. I think Google made that announcement very recently that Google Colab Google AI Studio, something like that's going to be free for 1 year. So I would say that just use that, go ahead and subscribe for it and use for all this exploration actually. So again, data key takeaways: data quality is your highest leverage decision. A 1.3 billion model on textbooks beat a 540, which is 400 times the model, is very, very important. Data strategy is an experiment loop, and make sure that you follow all these things, iterate, and then until you get your golden data. Feed the model for its job. Pipeline SLMs can skip general English, generators cannot. Right? So synthetic data augments, never replaces. That's very, very important. But where is that? I don't. Okay. So this is the paper that I was talking about, the one paper that I want everyone to read. The textbooks are all you need, 5-1. That's about it. But there is one thing that I was talking about, the 2000:1 ratio. Did I miss that somewhere? Okay, don't worry about it. I think there is one model that if you want to take a look into it, which is the Llama style, I think 7 to 8 billion parameter model. But if you see that they have, like say if it's 7 billion parameter model, let's make it like 2000 times. That's the kind of a token size that they have selected for the model training. So it was like 2000 tokens per parameter. So that means 20 tokens per parameter is the chinchilla loss. So when you say 2000, which is like 200 times increase, right? Tokens per parameters. So the mini CPM, which is 192 tokens per parameter, but here it is 200 times increase there. So that's a very important consideration that you should have. And I think somebody asked a question about unit, right? Can you come back with that question again? I think I'm done here. In case of any questions, you can let me know about it. But here you just have some. Sorry. 20. Yeah. So these are papers available. Yes, I think pretty much we are covered there. Yeah. We'll lead to the next session, which is on BP, fast text, and mean hash. Okay. Rajvi, can you read that question once again?
Yes, can you, there is another question. Can you help understand the kind of events need to be built for any sample target job?
I mean, again, so that's, see, there are a lot of permutations and combinations, right? Like depending upon your target use case, what kind of model that you're trying to build on. It's like a math model, a reasoning model, code models, or some kind of classifiers. A lot of things like that. You have to be a little bit careful about saying that what kind of evaluation suite that you should come up with. But if you set your evaluation suite before you go ahead and hunt for data, that would be very helpful for you. Maybe I can try to see that if there are any readily available evaluation suites available that you can do it, or you can do a custom evals. But I mean, it's easy to write your evals for your data strategy perspective. So
how should we decide how many parameters we should have in our SLM?
yeah, so you saw that mini CPM is like 192 tokens per parameter, and I talked about Llama style models was 2000:1 ratio. I would say that the ablation study will help you to understand what level of how many tokens per parameters that you need actually. So as you mentioned that the small proxy. So before you go on to a big bang approach of 1 billion or more than 1 billion parameter model, do it at a smaller version like million parameter model. Check it out, change your data set one at a time, and then explore that. It's all about experimentation. There is no hard limit saying that, or at least there is no like maybe Chinchilla loss, right? Like likewise, we do not have anything like that for SLM today. I would say that it's at your disposal.
How small can a model become before the performance degrades?
But don't go below that 20 tokens per meter. That's a scaling loss, right? Don't even try that. I would say that because it's not going to be very helpful. Keep that. That is a minimum point or minimum threshold that you should have it. Make sure that that will not degrade your performance there, but you can go anything above the 20 token limit.
Should we consider tool calling and JSON support? If so, what kind of data we need to consider for training?
Yeah, that's right. So the SLM, the model is one part of the equation. The tool calling or like some different agents are available as part of these things like that. That can be helping you in terms of setting the context and then feed this into one model. So that's again a deployment or engineering part of it, right? So how are you going to come up with that architecture to serve for your users? So RAG pipeline and things like that, you can have it. But again, I gave an example of what should be in the part of the pre-training, what should not be in the part of the pre-training, right? There are some information that you can augment part of your application perspective, but not part of the model perspective. So that's something that you should be thinking about it. What should be part of that pre-training and what should not be part of the pre-training. Okay, I think Rajvi, now it's a good time for break, I would
A
say.
break, yes.
Sorry, I took 5 more minutes, I should say. Sorry, Tavish. As a presenter for the next session, how much time that you want to provide for break? 5 minutes,
Let's not
10 minutes?
too much. I think probably 5 minutes max.
Okay. Sorry, folks, just have 5 minutes break and we will return back at 9:40, which is probably 7:10, right? Yeah, 7:10.
Yes.
Thank you. I'll stop the recording.
All right. I'm sharing my screen.
Yep.
Yeah.
Yep, we can see it.
Yeah. So we're gonna cover the tokenizer, fast text filtering, and main hash deduplication. A little bit about me. I am an intern at AI Institute of University of South Carolina. I generally have a solid understanding of language modeling, like the entire practice, though I, probably understand a lot more in the pre-training and architecture side, and I'm particularly interested in interpretability and safety. Till now, I've probably trained around 50 SLMs under the 1 billion parameter scale, including a few billion parameter runs. But beyond that, I also work with Airo, and I'm one of the co-creators of OLM, the library for training language models.
Kavi,
So
sorry to interrupt, but can
yeah,
you minimize the window above
which window?
the window which is over to the screen which is there. That
Oh,
can you
interesting.
minimize?
Looks like there's a bug. I don't really see any window like that. One second, let me check.
What is that you're seeing, Rajvi? Can you do a screen share again? Yeah, Dr.
Uh,
Deepak also
this
mentioned about it.
this should be full screen, right?
Yeah,
Yeah, full screen was there itself.
There's a
Okay.
top bar that's getting reflected. Yeah, I don't know why is that. Yeah, that didn't appear.
oh,
Yeah,
okay. On the right, Tavish, you see that this minimize, right? That single arrow, the line. Yes, that
Yeah. So,
is that fine
uh,
now, Dr. Deepak?
yes, yes. Thank you, thank you.
Yeah. Okay. Cool.
and I'm not sure if this top bar can be minimized.
No, it's fine.
That's fine. Now you're good. Go ahead.
Yeah. So I'm going to borrow a slide from Venkat. He covered this sort of 6 steps. Uh, in this lecture, we'll be basically focusing on the sourcing and curation. So curation, so that like when you sort of scrape a data set or a website that you know you have access to that is okay and you want to train on that website, how do you sort of technically, what are the sort of steps, the algorithms, and very specifically the algorithms that will probably help you scrape it and make it into tokens and vectors that the model can read. The other thing is that we'll be talking more about sizing the budget and like sort of the ways to at least the intuitions and the broad methods in which that you're supposed to use to ablate and freeze basically, right? So to do small runs that will help you predict your final performance. And sort of to, if you have a particular budget, how do you sort of account and make decisions that are informed uh, cost wise. So that's going to be covered next Saturday. Today we're only going to do the sourcing and curation. So the previous lecture broadly talked about how do you sort of choose good sources, uh, sort of general quality goals, and decide the mixtures. Basically, like I want to have 300 million tokens of Stack Overflow. I want to have 400 million tokens of Stack Exchange, etc. Right? That's sort of a mixture. But then uh, what we're going to talk about today is how do you sort of, once you download the HTML, the general broad way of extracting the article out of it, basic roughly filtering for usefulness. Uh, on the raw internet, honestly, you'll find like sort of some spammy articles that are duplicated like 5,000, 6,000 times across a lot of places to sort of boost engagement. And they can artificially sort of move our model or overtrain our model on particular parts of the internet that probably shouldn't be. Um, so deduplication is sort of removing that sort of junk. And finally, what we'll be focusing on a lot is tokenization because although the first three are really just engineering things you can learn on your own, tokenization has a lot of quirks, and these quirks can sort of have practical implications in the model that you train and its weaknesses because the model really doesn't read text, right? It sort of gets these embedding vectors. So we're going to first look at the algorithm behind BPE very thoroughly, then roughly go over how do you extract high quality data from web scraping, and then go over the min-hash deduplication algorithm. So let's cover tokenization first. Here I actually want everybody to sort of predict how many tokens does the model see, right? We've covered this previously that a model doesn't read entire words. It probably sort of unbelievable is broken down into unbelievable. So let's, for example, cat would probably be one token, while tokenization would probably be broken down to tokenization. So, probably if people could drop in chat how many tokens token would consume, space token would consume, 127 plus 677 would consume, and Hindi plus this, so the entire string, Hindi plus that emoji would consume. Maybe we can look at chat. Uh, can people, 2, 3, okay, 5, I see. Okay, that's a good. Does anybody else want to probably drop a guess in chat? 1, 2, 3, 3. Okay, that's a guess that most people would make. Uh, I think the results will actually be surprising to many people. Okay, then let's
A
actually
lot
look
of
at
surprises in today's meeting.
let's look at the GPT-3 tokenizer. I have it opened right here, and let's try each of these examples one by one. So let's first look at token. Token is one token as was first predicted. But if I put a space in front of it, that still remains one token. And the interesting thing is the token and space token are not the same token. And we'll probably look at why that is. So to a model, token and space token are actually like two completely different words. At least for GPT-3. Then 127 plus 677 is 4 tokens, and the way it's broken down is also kind of interesting. That 127 is one number, one token, and then space plus is one token. Then space 6 is one token, and 77 is one token. That sort of behavior also looks a little, weird. And we'll probably see why this happens. And finally, this text, Hindi plus laughing emoji. We'll probably have to copy that. And this is 13 tokens, actually. Instead of, in English, this would have been far fewer tokens. Like 5 tokens, right? Even the word Hindi in Hindi is 10 tokens, while in English it's 3 tokens. So this is the sort of interesting behavior of tokenizers that we'll try to understand through the course of this lecture. So tokens are the model's actual inputs. You sort of, if you have the word unhug, perhaps it'll be broken down into un and hug, which un could be token ID 421 and hug could be 1832. Basically, a model like GPT-2 probably wants to read sort of numbers, and what you do is you take the vector for un from the embedding table, which would be on row number 421, and sort of you just extract that vector, and then for hug will be row number 1832, let's say, and then you extract the vector for hug, and these two vectors are what the model will be reading, right? So as we saw, attention takes an n by d input, where n is this amount of sequence, and d is the depth, is sort of the embedding vector. The embedding vector comes from the table, and that n is determined by how we tokenize, right? N is the context length. So if unhug was one token, then there would be one vector for it. Otherwise, now there are two vectors. Right. Now let's also look at some interesting other behavior from, and let's probably try to understand why it is important to understand tokenization and why it can lead to real quirks from very powerful models as well. For example, and this might be very surprising for many people as well, is let me show you an example. Yeah, this is actually asking GPT 5.5 and GPT 5.6 Soul to reverse unbelievable in spelling. And it would be quite surprising, but until 1 or 2 months ago, GPT 5.5, which was, 5.6 Soul was released 1 or 2 months ago. So the best model till, let's say, 2 or 3 months ago was this model, GPT 5.5. And it is not actually able to reverse unbelievable in spelling. This is unbelievable. The 5.6 Soul is able to do that. And this sort of weird behavior is also because the model doesn't look at alphabets, it looks at tokens. And so a lot of model behavior quirks are actually explained by sort of the tokenization method. Early models were also really poor at arithmetic, and like GPT-3 will very, very often have problems with code, even in indentation, actually. So this is actually another quirk. If I look at the GPT-3 tokenizer and I say def func 1, 2, 3, 4, ignoring everything else, the 4 spaces here actually, instead of being one indentation, there are 4 separate spaces. This is clearly not efficient because you're taking up four spaces where there should be one intent, and that actually takes up extra context length. Where if you compare GPT-5, this model actually does have that fixed. So there is indentation. There's a separate token for that. So what we're going to do first is sort of understand the algorithm itself and then understand where it sort of breaks and when you're going to build, and we'll look at very good reasons for building your own tokenizer instead of inheriting what OpenAI has. And when you do build your own tokenizer, all the places where things usually fail and probably what you want to do to sort of make sure you mitigate those failures. So basically the need for a tokenizer, a BPE, a byte per encoding tokenizer is sort of that if you were to tokenize entire words, then your vocabulary is huge. Like English has about 500,000, 5 lakh tokens, 5 lakh unique words. But if you were to like include Hindi, Japanese, Chinese, and a lot of other languages, that can get quite high. And so what we probably want to do is not have such a big vocabulary because it's sort of very difficult to train a huge vocabulary. The other problem is that when something is not part of the vocabulary, like tokenizability, which might not even be a word, you are not able to encode it at all. And if we were to instead use like word tokenizers, then sort of the problem is that each of these alphabets will take up one space and they're able to represent everything, but the context, the amount of positions they take is really high and they fill up the context window. Sort of a context window is, like how if you have a coding agent, it probably starts summarizing after a point. That's because it can only see a finite amount of tokens and spelling things out would fill them up very quickly. And the thing to remember is that attention is an O of n square operation. So you don't want to make really, really huge context windows because that will create a square cost, not a linear cost. Right. That's why sort of the idea of subwords is a very like reasonable and good method. It sort of is somewhere in between of word and character level. And as you can see, like unbelievable gets broken down into unbelieve and able, but the same belief can be reused for believer, right? And the thing to keep in mind is that these chunks are really, really based on what the model was trained on, right? So believe does not exist as a word here, right? Believe exists as a frequent group of alphabets, right? If unbelievable existed as a single word, it would have been tokenized as a single word. But since it doesn't, it's sort of broken down into these individual pieces that are available in the vocabulary. And then you sort of send each of these individual pieces. And then the pieces are created by how frequently they appear in the dataset. So this practical compromise of BPE is between a tiny vocabulary, which fills up the context window too fast, and a huge vocabulary, which sort of has other problems with it that we'll probably discuss a little later. So let's go through the algorithm that builds a tokenizer. First, let's take an example of a dataset which has hug, pug, pun, bun, and hugs at these particular frequencies. So hug is in the dataset 10 times. The word pug is in the dataset 5 times. Pun is 12, bun is 4, and hugs are 5 times, right? And I probably just want you to think on your own. If we were to sort of start by tokenizing these based on characters only, on alphabets only. So if there were HUG, PUG, PUN, BUN, HUGS, and you were sort of able to mix two alphabets together. So maybe you were able to join H and U and G together to form one token. And if hug, instead of being HUG, was H and UG together, then instead of occupying 3 places, it would occupy 2 places. What would you probably want to merge, right? And sort of intuitively, it seems like this token sequence UG does actually appear quite often in the dataset. And if UG could be merged into one token, then that might save us some space, right? Let's just walk through that example now. So the base vocabulary right now contains of only these 7 alphabets that are sort of placed around in the dataset. And we have hug 10 times, pug 5 times, pun 12, Bun 4 and Hugs 5 times. And what we're going to do is we're going to find the algorithm. What it does is it looks at two adjacent tokens. So HU, UG, PU, UG, and calculates the frequency distribution of these adjacent tokens. So let's say we were to consider the example of UG. Though as hug appears 10 times, UG in the word hug appears 10 times. Then UG in pug appears 5 times, and in hugs appears 5 times. So totally the UG sequence appears 20 times. I hope this is clear up to this point. Okay. Now, once we got this, what we're going to do is we're sort of going to merge. We're going to sort of make the frequency distribution for all pairs. So UG, PU, UN, all the possible next tokens. And as UG is the most common next token, what we're going to do is we're going to sort of, I guess, try to merge, and that's what we'll do. Since UG is the most common sequence, we'll merge UG into one token, and HUG will become HUG. PUG will become PUG, right? And so a sequence like hug, which was 3 tokens long, is now actually 2 tokens long, right? If this is understood up to this point, I think if everyone could just drop a thumbs up. Actually can't see them, so I hope it's clear. Or
Yes,
questions?
yes.
Okay, it's good. All right. Now, once we got UG as a new token, we have to add it to our vocabulary. So our vocabulary was initially only 7 alphabets. Now UG is as a separate token itself, right? We're going to repeat the process again. We count the frequency distribution, and we see that U and N is a common co-occurring sequence of letters or characters, and then we're gonna merge them, and we create another new piece in our vocabulary. So PUN becomes PUN, and therefore 3 characters again become 2 characters. Now, the interesting thing here is that the next most frequent merge is actually H plus UG, which because H plus UG appears 15 times. And that means we are actually missing 3 alphabets into 1 token. But for the algorithm, it's actually just at the algorithm at all points. All it does is merge 2 tokens into 1 token. And those 2 tokens could have any number of alphabets, but the algorithm is very consistent. It takes 2 tokens that appear very frequently together and merges them into 1. And therefore, we're able to sort of have U plus G as UG, U plus N as UN, and H plus UG as hug. And the thing to keep in mind is that this is actually a ordered rulebook, right? Because you can't mix H plus UG until UG itself exists as a token. So UG needs to be defined first, and then H plus UG as a merge exists after that. That's just a thing to remember and keep in mind. Now, what this means is that sort of once you'll train your model, right? You train your tokenizer. If you're going to deploy a tokenizer in, let's say, if you're building an agriculture model, you will train your agriculture model once on agriculture related tokens. And then once you have the merge order ready, you'll start with their alphabets and then repeatedly merge things, right? Example would be this. So we never saw the token unhug, but what we'll do here is the first thing in merge order was to merge UNG. So UG get merged. The next thing in the merge order was to merge UNN. Then UN get merged. And finally, H and UG were to be merged. And then HUG was merged. Therefore, unhug was broken from 5 tokens into 2 tokens. This is the sort of merging and merging loop until a word is sufficiently tokenized. Right. Now that I think we have a solid understanding of how tokenization works, the algorithm, BPE, the way it's trained, we're gonna look at places where tokenization has a few quirks, right? So first of all, since for a tokenizer, everything is a character, and a UTF character, that is. So not even a so these are not words exactly. Since they're all UTF characters, space is not treated as a separate uh, thing, that these are words and these are not words. Space, like any other character, gets merged, and therefore hello and space hello are treated as separate tokens, which is just a kind of a weird quirk. But that's actually not completely consistent, because I think it makes intuitive sense that hello and space hello probably should be the same token and not use a vocabulary. There are many tokenizers that don't do this, but let's say, but GPT-2, GPT-3, and I think GPT-5 also uses the same method. Um, so this is something. The other thing is that uh, what I showed earlier was that you were merging characters, but these are sort of what you actually do is merge bytes, right? So UTF-8 bytes, where let's say 67 byte, only 67 byte corresponds to capital A or something like that. But later, let's say the way UTF-8 works is that sort of you use 1 byte for very frequent English words, but usually Hindi, Chinese, Japanese, etc. sequences, they actually use more than 1 byte. They sometimes might use 4 bytes, something like that. So that means that a English sentence, a Hindi sentence compared to an English sentence has much more bytes. And since you don't really care about if 2 bytes or 3 bytes or 4 bytes together are part of one character, or are they multiple characters, very often you'll see that many tokenizers will not merge different bytes into one from Hindi. And therefore, the coverage of Hindi, Chinese, Japanese, Kannada, any non-English language will be very poor, because this is based on UTF-8. This is one of the reasons to probably make your own Indic model. Because and so that it probably doesn't consume as many bytes and is as poor at tokenization. Because as we saw, Hindi, which is for anybody who knows sort of Hindi, would be about 3 to 4, let's say, or 5 characters, right? In English, most words will actually become one token, but this one Hindi word was something like 10 or 8 or 9 tokens, because each of those characters itself use so many bytes, right? And so that means that though all languages are representable, because at the end of the day, they're all just bytes, and you can represent all bytes individually. And that's one of the really good things about BPE, is that you can never have an unc or unknown token. Or actually, you can, but it's very, very rare, right? In almost at least all UTF things, like Hindi, English, all these languages, all these emojis, since they're all in UTF-8 sequence, they're a sequence of bytes, and you can, if there is no token that merges a lot of these bytes together, you can at least represent them as raw individual characters. That ensures that coverage is very, very high, but efficiency is usually not that high. So if you are dealing with sort of different languages, there is a point in training your own tokenizer for that purpose. The other thing is that you do want to make sure that if you are dealing with a lot of code, that you have managed indentation in a reasonable way, right? Whatever that may be. If that means ki you have one token for indentation, or one token for 3 spaces, whatever that is. This was covered as previously seen. The good thing about BPE is that it can represent any UTF-8 sequence. So even a wave emoji, which is sort of a sequence of 4 bytes, the basic thing that's always done is they're represented as 4 bytes, and then merges happen. So if a merge happens, that's great. But at the end of the day, you can always represent any UTF-8 text. And finally, this is why most people should train their own tokenizer, is sort of that, let's say, I think the GPT-5 tokenizer has about 2 lakh vocabulary size, and GPT-2 has 50,000 vocabulary size. And, in a SLM, which is about, let's say, 500 million parameters, 200 million, 300 million parameters, there, even the vocabulary size can take up, maybe 30, 40 million parameters. And the thing is that if you are training an agriculture related model, right? You don't need a token for def, return, indent, precedent, Taylor Swift, something like that, right? You probably need a very small set of tokens. And that can be a point where you can sort of save a lot of model parameters, and also make the gradients a little more tractable. So probably instead of having a 2 lakh vocabulary size, probably a 10,000 vocabulary size is okay for a domain model because it doesn't need to know everything about all words out there. And for the rare words, it can still represent them using bytes. So you don't lose out on coverage. You only lose out on efficiency. And so in general, a vocabulary size will trade sequence length for embedding parameters, right? If you have a large vocabulary, then you'll have shorter sequences, but uh, uh, the embedding parameters themselves are dependent on your vocabulary size. So that's going to increase. And sort of an analogy to that is that more words in a dictionary will require less description to explain something. Like if your vocabulary like if you're trying to explain something and you have the word tranquility, it does save you that sort of thing, but the dictionary does become larger and it's a little more difficult to learn in a more mathematical way. It's just that if your vocabulary size is so big and you don't train for enough tokens, very rare words or very rare tokens will will never receive or will very rarely receive gradients and probably won't be able to learn much. That's one of the problems. And one thing to always remember is that you want to shape your tokenizer with your model completely frozen. Any change in tokenizer will change what embedding row you take, and that will completely change the model and its performance. The other thing is that almost all models in deployment will have a set of special tokens. These tokens are sort of like start of sequence, end of sequence, or like user question, this, and then user response, right? And they're specific to each model and depend on specific functionality that you want from your model. Okay. So that was about tokenization. Let's briefly go over extraction data filtering. So this is what a typical web page will look like. It's gonna have a title, lots of links, cookies, except buttons, and training on this kind of dirty data compared to training on clean data will very, very significantly boost how sample efficient your model is. Model trained on poor quality, dirty data, which is not filtered well, will have poor sample efficiency and will require much more data volume compared to when you clean it very well. So you want to clean things, and the way you clean will really depend on which site you choose. The general methods sort of are about going through the HTML, figuring out where text is located. So you sort of make a map, right, with like sort of a tree structure, and go through each part, go through all the divs, and try to find out where there is a high ratio of sentence to code and very low code, and sort of where you see the highest amount of sentences and language structure possible. That's probably where you have real data within the data set. To check if something is language or not, you don't have to always use an AI model to judge that. Very simple methods can be used, like a dictionary of the 1,000 most frequent words and how many of the most frequent words are actually in the text, or some basic proxy of judging if there is language. And sort of once you have the general idea of where text is located within that web page, then you can sort of clean out code, remove in usual HTML, remove anything within two greater than lower than symbols, where let's say there's bad bytes or some clearly disformed stuff. Very often when there's a lot of white spaces, that can be removed. But that's probably where one place you want to take care is that if it's code, then white spaces do have a lot of meaning. And you want to make sure that the amount of processing you do is really dependent on what kind of data set you have and where you're filtering from. So in a blog, removing white spaces is completely fine, but in code it's probably not. A lot of text can be repeated. Sometimes you can tell that something is spam if there are too many words, which probably aren't going to be in practice in real life. So this is a very engineering heavy process. You decide, let's say, I'm going to scrape Stack Overflow. Once you have it scraped, uh, there's a lot of case by case basis and deliberate engineering that needs to be done to remove and extract the real text. Once that's done, it's still not clear if it's useful. Like the internet is full of, like, let's say, advertisements, affiliated programs, etc. Where, for example, you might see something like a miracle food melts weight overnight, and that's probably something you don't want to train on, and that's poor quality data. While oats containing 13 grams of protein per serving, that's high quality data. That's the data you want to keep. This is where using a AI method is going to be useful. In all these kind of things, it's probably better and cost efficient to not. Once you have some filtering done, here we can use some sort of AI method. But we probably, one thing is we can't filter it through it ourselves, and it might be too expensive to use an LLM to do this because, filtering to 10 to 15 trillion tokens is a little expensive. So we used fast text filters, which are simple linear models that sort of are able to make decisions on if to keep or not keep data. The general approach from a top level is basically any piece of text is broken down into sequences. These can be sort of n-grams, which are like a bigram will be a sequence of 2 characters, or they can be broken down by tokens, whatever that method is. And after breaking it down into those n-grams, they're run through a embedder, so some model to embed them, and finally a classifier is trained to predict if the data should be kept or not kept. So maybe 500 examples you can manually label and see that these are sort of the data I want to keep. This is the data I don't want to keep, and accordingly, each sort of n-gram can vote on if to keep or not, and you can get a score for that web page document. And finally, use a validation set to find out the cutoff, right? What data do you want to keep and what data do you want to leave? There's a simple classifier that classifies based on keeping or not keeping based on a few labeled example, and that takes an input, some embedding method that you can probably just use word2vec or some very existing embedding method. But the one thing to keep in mind as a practical engineering thing is that if I'm trying to sort of extract Stack Overflow or coding data, I don't want to use the same thing to extract agriculture data, because since I've evaluated my classifier on one kind of data, you want to make sure that you don't change data distribution. Otherwise, the ratio of false keeps and false drops, and your general model accuracy will drop a lot. So try to keep the model as in domain as possible, and try training multiple classifiers. Or if you can afford to, then you can just use an LLM to do the labeling. But I think that usually becomes a little expensive. Finally, let's go over the deduplication algorithm called min-hash deduplication. Very often in the internet, lots of articles, especially many, many spammy ones, are repeated like 400, 500, 5,000 times, something like that, across a lot of websites that are also not really popular or can be a little scammy. Or there are other reasons that articles are repeated, like very popular articles are also repeated across many, many websites. And you don't want the model to be skewed towards some data and not towards others. And so deduplication is a generally followed thing, and it's shown to have significantly improved sample efficiency. Sample efficiency in the sense, when you train a certain amount of tokens, how well does the model perform? And this deduplication does help in that quite a bit. The problem is that you can't check if 2 pages are the same character by character, simply because first of all, that's an O of n square operation, because you need to check each page with each other page, which is not possible. And the other problem is that 2 pages can be very, very similar. Like in this example, can have 5 written in alphabets versus 5 in the number, or in practical example, have a few extra byte spaces or have a bit of extra HTML code that wasn't stripped out. And that can that can, sort of make up, let's say if you're using a hash to check if two documents are the same, an exact hash will not work because there will be a small amount of difference in most documents, but that doesn't mean that they're not effectively the same document anyway. So you want to sort of find a method of at least approximately finding similar or like almost the same document and sort of deduplicate and remove them. So one method of doing this is using a Jacquard similarity. What you do is sort of look at two consecutive words, right, in both sequences, and sort of compare. So what I've done here is simmer oats for. You're taking two consecutive words and making groups, and seeing how many of these groups are shared versus how many of them are out of all of them, right? So out of this, so there are 9 of these groups, and 5 of them are shared, right? And this sort of is able to show that though only 5 was replaced with the number 5, these two are the only ones that will be affected. All these other sequences will be common between the two articles, and therefore we will be able to judge that they are similar articles. And this is how you're able to compute a Jacquard similarity score. The problem still is that this is still an O of n square operation, right? Because you're taking two documents and comparing their subwords. So we sort of want a general method, right, where we can make a fingerprint of a document. And once we make the fingerprint of the document, we can check similarity between that fingerprint and any other fingerprint, and that comparison can be very easy. Even though that's sort of still O n square, that comparison can be very cheap. And sort of the way we do that is, let's say we take any random sequence of two words, any random ordered sequence of two words from page A, and we check if it's in page B, right? In all likelihood, it would be. Like, usually it would be, except for the case of 5, because for 5, that sequence, if it's in page A, it's not in page B because page B has the number 5, right? So, sort of this interesting intuitive result is that the expectation that, and so the other thing is that checking if strings are similar is very similar to checking if their, hash is the same. So, the interesting thing is that, and this is, I think, very intuitive, is that the probability that a min hash will match, so a random min hash will match, is equal to the Jacquard similarity. And min hash deduplication uses this property to check if two documents are very similar, because you can sort of make a fingerprint for a particular document and then compare the fingerprint across documents and use that to judge. So let's say the practical method that people use based on this intuition is that for a particular page, you will probably try 8 hashing functions and get the lowest sequence hash. So let's say page for hash function A for all the sequences in page A made a list of different numbers, right, corresponding to each sequence. Just take the lowest hash. If page A and page B have the same strings, then their min hashes will match. I think this is a little difficult to understand. And it's okay if you don't get it, because this is an algorithm and it's not that important. But let's try to understand it anyway. The idea is here that if for a particular hashing function, right, if page A and page B both have the same sequence of 2 letters, of 2 tokens, then for the same hashing function, both of them will return the same same sort of value, right? Let's say that hashing function will return a value of 17, right? And if that was the lowest among all the examples, then you will find that both of their min hashes will match. Does this sort of make sense? I think if it makes sense, you can drop off thumbs up. If not, we can go over it once more. Rajvi, I can't see thumbs up, so you can let me know if.
Yeah,
Yes,
we
I
can see
think we
that.
are
Yes.
fine.
Yep.
Okay, so I think okay. So
And Tavish, I just want to remind you also there's like about 8 minutes left. So yeah,
okay.
just letting you know.
So that's about it. Basically, because of this, we are able to make a fingerprint of each document. That is the min hash for different hashing functions. For 8 different hashing functions, the min hash is going to be the fingerprint for that document, and you can compute similarity between different min hash signatures. Based on this, you're able to at least get pairs of documents that are very likely to be twins. And then you can actually calculate a very exact Jacquard similarity, because let's say out of 1 million documents, if I know that there are these 700 which are similar, then I can do an O square operation on the 700 documents instead of doing it on the 1 million documents. And then I can probably do the quality checks and keep only one of those out of the 700 copies. So just doing a recap, we take a very dirty page, we try to extract the text out of it, use a linear classifier to figure out if we want to keep it or not, use a min-hash deduplication plus Jacquard if you want, Jacquard similarity for higher precision if you want, and keep only one of multiple copies. And finally, train a tokenizer that is highly specific to your use case, your language distribution, your domain, and a vocabulary size that makes sense for your model. If it's a 200 million parameter, then it doesn't make sense for it to have 50 or 60 million tokens of vocabulary size, right? It's a big waste of space. And on your particular domain, you decide to train a tokenizer, and that tokenizer should represent a diverse enough distribution, right? Of tokens that you want to exist, and you want to spend time to make sure that reasonable tokens that should exist in your dataset actually do exist, and then they can be converted into embedding rows. Okay, I think now we can take questions. I'm stopping my share, or I can open the chat line. Yeah.
Sounds good. So just before getting to the questions, Rajvi, like I think, did we place that the guide that you prepared in terms of a data strategy?
Yes.
Can you paste the link in the chat line? That will be very helpful.
Okay.
Can share my screen, and probably like this is the document that was prepared. This is covered in different parts. Like part A talks about that 4-stage pipeline, going from source discovery to quality enhancement and evaluation. And then the part B talks about knowledge graphs and neurosymbolic AI. So again, so this is an active research that we are doing at AISC and IRO in terms of bringing that neurosymbolic way of creating that SLM. So this is definitely a good part to take a look into it, but we can focus more on the part A perspective. And there's also other information that you wanted to take a look into it as well, domain-specific data strategies and so on. Rajvi, is there anything that you wanted to provide any kind of overview about this one? Any comments from your side?
So I think here I have included domain specific evals, what all should be explored and how they can go ahead for it. If any questions, you can put it in the Discord and I'll be answering those. And we
Exactly.
have the neurosymbolic and the generic SLM both included. Whichever you want to explore, you can explore. The neurosymbolic one is something which we are exploring at IRO, but yes, that is something which if you are interested, you can explore.
Exactly. Yeah. Okay, and this link is available in the chat line, and we can
I'll be
definitely go.
posting in the Discord and will be putting in the folders which we have given for the days. till now. And
Sure.
also one more announcement, like for day 3 yesterday, Mohit has given a Google Colab notebook. So has anyone tried out? Because the solution we have not yet posted. So you can compare the solutions, but we will be putting out the solutions once you are done, and then we will be putting that for you to compare the solutions. Yes.
Okay. Before I can just hand it over for questions. But Dr. Deepak, I think you asked a question about why Chinese AI models are cheaper than that enterprise, the US models. I found a very good article that explains that. If we get time, we can discuss more about it. But otherwise, I'll just share this link in the chat line, and a
Yeah.
picture of that will be very helpful.
Sure. Thank you. Thank you.
Cool.
I just
Over
wanted
to
to
you,
answer
Ravish. Go ahead.
the question raised by Dr. Deepak. Actually, I've seen two approaches. One of them is that you sort of match exactly the inference, the tokenizer training distribution with your target distribution, which is like, let's say, if I mostly want to have agriculture data, then I'm going to train on agriculture data. So that for your dataset, it takes as little context length as possible for your vocabulary. But this is not actually what most frontier labs like OpenAI, etc. do. Llama. What they do is they'll train a more diverse dataset for their tokenizer than their actual data. And they do this because, let's say, if in their actual data, Chinese is only like 2% data, then it is then if they train a tokenizer on that, then it is very unlikely that you'll have Chinese tokens in your real model. And that means throughout the model's life cycle, it will be significantly worse at Chinese. So very many, I've seen most frontier labs have mentioned they sort of try this other thing where the tokenizer distribution will try to be a little more diverse. Will have little more multilingual data than their actual true data, so that they're able to support foreign languages better.
Yeah. Thank you, Tavish. So that holds good for within the training set also, right? I mean, say for example, I have some 1 million tokens for training, and basket them as 1 million different diverse tokens that I have for training. All 1 million tokens should have more or less like equal representation in a training, or is it fine as the data comes by?
I think for a domain model, it's much more, it's okay to train your tokenizer on the same data that you'll actually train your final model on, if that's what you meant to say. Or I maybe didn't get your question.
What I meant is, say, suppose next token predictor, whatever the model that we want to train, I have 1 million tokens, let's say, right? 1 million different token size that I've taken. And there is certain amount of training data. That 1 million token corresponds to different frequency of occurrences in the training data itself. That distribution, should it be uniform or more or less or is it fine like if there is some skewedness in the given data? The training part I'm talking about.
Probably should be uniform for a domain model. People, as I mentioned, some labs will try to keep it deliberately non-uniform, and that is for very specific engineering purpose, like allowing multilingual data. But if you want to make let's say, I'm taking the example of an agriculture model, then try to make as uniform as possible, because that will guarantee that when you actually deploy your model in inference, that for your given vocabulary size, the context length is as optimum as possible. Otherwise, you might, let's say, for example, a word like, let's say there's a word like tranquility, which was very, very frequently seen in your tokenizer training, but in your actual model, it is never seen. So that's sort of a wasted token, right? So probably avoid skewness and keep it as uniform as possible.
Okay. Thank you. Thank you.
I know we're at the top of the hour, and if there are any last question, we can take it.
Yeah, hello. Am I audible? I had a
Yes.
question. Yeah, so Tavish, when you were speaking about the BP tokenizer, so let's have a very large document. And like, where do I know when to stop that tokenizer? Because like after a point, you'll just come to a point where, every word has become a token if we keep going in the same loop over and over again.
Right. So what happens, you will decide a vocabulary size and you will keep merging until you stop, until that vocabulary size is hit.
But then let's say like if, for example, prepositions, like, I have a lot of prepositions present in my in the corpus which I'm giving for training. So like, won't they just take a large chunk of my vocabulary size, and then, I could have rather saved or, use it in a better way if there were newer words which could have been combined into a token instead of, giving prepositions as one token each.
Absolutely. That's I guess a thing where you want to be careful. If it's an algorithm, so you probably want to make sure that you don't train it on just a bunch of prepositions that are following each other, and you don't. And it would be bad if, let's say, in on becomes a token, which is not semantically useful. So that's the point of trying to make your tokenizer training distribution match your model training distribution, and certainly it will keep doing merges until you hit your target vocabulary size. So that's just the way the algorithm works, and it can have problems.
And like one last thing, that is there a ratio, like if I'm training let's say 100 million parameter model, so is there a ratio on what size should my tokenizer size be on an approximate level?
In all large language models, the tokenizer size is almost negligible compared to the model. Like it's probably, I don't have the number on my hand, but it's something like 1 to 5%. But on smaller models, that can become quite big. So your embedding parameters are going to be D by vocabulary size, and so they should be ideally not too much, right? Because they don't really necessarily help in the forward computation. You can probably look at these numbers, look at what's, let's say, Kimi K3, what the embedding parameter size is.
Understood. Thank you.
So
No,
Tavish,
we
I
are
just have
over
one
time
question.
right now, and probably we can take questions in the Discord. I know it's a dinner time. People will be waiting probably. So I would just close the session. And then if you have any questions, we can definitely discuss in the Discord channel. And I think somebody asked about the missing assignment. I'm probably, Rajvi, I think we have this in the Discord channel. So you can follow along in the Discord channel for your assignments and stuff.
So
Venkat,
Venkat,
I just wanted
can we
to,
have like 2 minutes of time right now for a clarification?
Can you spend another 1 minute? Yes, let's go. Any questions on the assignment?
Yeah, actually, if I want to clarify one thing on the Deepak's question that he was actually asked. He mentioned shall we consider that the token uniform distribution or not for beta training purposes or similar. So I would like to clarify one thing, as Tavish mentioned right now. We should follow a uniform token frequency distribution. But say given that Deepak's example, he mentioned 1 million training tokens are there. So accordingly, the common training tokens are appearing very frequently. So that our higher counts will be there. Rare tokens will be appearing less often. So I think I may be wrong. From the BP section, the frequency actually repeatedly marks the most frequent adjacent pair, if I'm not wrong. And to me, the token frequencies must not. It's not necessarily be uniform, but we need to make sure that there is no excessive skewness or the coverage is sufficient enough. Am I right, Savish?
Yeah, absolutely.
Yeah.
What I meant to say is
the data or domain mixture balancing is more important here than the uniform tokenity, right? Token level uniformity.
Yeah.
Okay. Yeah. Thank you.
I just wanted to mention about this week's work. We're going to be training Qwen. We're going to be writing the code for Qwen 3, Gemma 3, and Phi 3. It's open if you want to write this with PyTorch or ONM. We'll be conducting tutorials for both of them on Tuesday and Thursday. Thursday, I think timing has been confirmed. Tuesday also will confirm. So those will be extra sessions, sort of more walkthrough tutorials of teaching OLM and PyTorch so that you're able to write code for both of them.
Okay, so session's timing is around like in the evening itself?
Yeah, those things will be communicated in the Discord channel. I think follow along in the Discord channel. And maybe Rajvi, we can just send an announcement to all the participants if somebody's missed here. That would be very helpful. Yeah.
Yes.
All right. Thank you so much. We are over 6 minutes, but thank you so much for staying late. It's a very good productive session for today. Thank you.
Thank you. Bye-bye.
Have a good day.
Thank you. Thank you.